Hey, it's Mr. K doing a video for AP Physics 1, talking some simple kinematics as an introduction to the class. And here we go. Let's start off with some basic terms. One is displacement. That is just a change of position overall. And then the other is distance. That is the total amount that you are going to traveled. There you go. I guess I got distracted with that. Anyways, traveled. So a displacement is basically a change of position, which means I'm going to start at a location, I'm going to end at another location. I don't really care what happened in between. All I care about is the difference between the start and end points. So if I wanted to talk about the displacement between dot 1 and dot 2 here, or dot A and dot B, then I just displace myself 1, 2, 3, 4, 5. So my total displacement, and this is the horizontal axis, I'm going to use X, is going to be, again, 1, 2, 3, 4, 5 in the positive direction. And if we say a certain unit, we'll probably say meters here. Now, if I did not just travel straight from A to B as the crow flies, I could go all like this, and around and backwards and in and then probably down like that. And so while my overall displacement is still positive 5 meters in the X direction, well, my total distance, if I wanted to talk about that, would be much greater than 5. It's going to be, I don't know, if I try to just take this string and stretch it out, maybe around 8. So, definite differences between displacement and distance, and we will use those in different spots as well. To get from A to B, it's going to take a certain period of time, and that time is going to be where we would use the velocity or speed terms. And so if we have a displacement and a time taken, or a distance and a time taken, then we are going to use either velocity or speed. Speed, it's more basic of them, is going to be the distance traveled divided by the change in time taken to get there. Now, velocity sounds a lot like speed. Sometimes it's used interchangeably, but really there is a difference. Would consider the displacement over the change in time taken. And we're also going to put in a direction here, so adding in a direction. I'm kind of running out of room, so I'm going to leave that off. So speed is a distance over time, velocity is a displacement over time. So let's say that we took, I don't know, somewhere around 10 seconds to get there. So if my change in time is going to be a total of 10 seconds to make the motion from A to B, then that means I can talk about the speed of it, and the speed for this problem would be a distance of 8 meters divided by a time to take of 10 seconds, which would be 0.8 meters per second as my average speed for this time. Now that doesn't say that we can't like start and stop in between. We can, but we're just talking about the average speed in this case, as well as the velocity, the average velocity. So if we wanted to talk about another word, instantaneous, I guess I'll write that down up here, instantaneous speed or velocity, that's going to be the velocity or speed at a very, very specific point in time. And so we would have to look at exactly what's going on at that particular time and see how fast you're going there. Overall, though, if you wanted to just find the averages, it would be the overall distance or displacement divided by the time. So this would be your average speed. Use a little subscript. And the average velocity would be given by the change in position, displacement over that time. That's 5 over 10. That's going to be 1/2, or we'll just say 0.5 meters per second. And that'll be your average velocity, average V. Okay, so we will be using those things very frequently throughout physics, more so the velocity term, less so the speed term. But let's keep on moving on. In order for us to get from here to there, if we started at rest, that's kind of important, then we would have to speed up, and if we ended at rest, then we would have to slow down. And so another basic term that we will always use is going to be one called acceleration. And you've heard of it. You might have even heard of deceleration. Deceleration is just acceleration the other way. So acceleration would be the proper term either way, just positive or negative. And acceleration would be a change, delta, of velocity over a change in time. Okay, so that would be your acceleration. The units of these things whereas displacement has units of position, which would be like meters for us. Distance has units of position, well, length, which would be meters for us as well for the most part. Your speed is going to be your distance over time, so that's going to be something like meters per second. All right, so we'll just put like m over s if we were writing down units here, put brackets around it. Same thing for velocity. Velocity is going to be your meters per second, your displacement over time. Now, acceleration is going to be units of changes of velocity, which are already meters per second, divided by changes of time, which are in seconds. And so the units for your acceleration would be the meter per second, or the meter per second squared. Okay, and that will be a constant thing. The best way to probably say it to where it makes sense is meter per second, or usually you'll hear it as meters per second squared, but don't let that square throw you off. All right, so an acceleration is any kind of change in velocity over a change in time. And so that term will be used in many, many different problems. And let's go ahead and give you one to start. And so we'll talk about all these things with this problem. Let's say we have our bowling ball. We started off in class with our bowling ball on the cliff, but we'll give you a little bit more difficult one. We will say that this bowling ball has an initial velocity in the upwards direction, and that velocity in the upwards direction, I'm going to say it's about 10 meters per second. Okay, that is our initial velocity for this problem, or V naught, if we will want to say it like that, or V0 for very start. And we're going to say that we're going to let this bowling ball go for about 3 seconds. So the total change in time, our t-tot, will be 3 seconds total. Now, in these 3 seconds, this bowling ball will be doing multiple things. And to really start off, let's just talk about what it is doing at the very start. So at the very, very start, we know that it is not at rest. It is moving at 10 meters per second. So instantaneously, the velocity would be 10 meters per second upwards. So we can say that. All right. As this bowling ball goes up, if you throw something up into the air, it's going to probably stop and turn around. So somewhere up here, the velocity should be 0 at max height. So I'm just going to put max h. All right. After it hits max height, it's going to turn around. It's going to start to go down, down, down again. It's going to reach this part of the cliff, and then it's going to keep on going down past that, most likely. And we're going to look at all those cases and try to just talk about it and not necessarily use the complex-looking equations that you might associate physics with. All right, so for 3 seconds, that's the motion of this object. It is after we have let go of this object. Don't worry about the forces that are acting on it. Before we get this thing moving to 10 meters per second, we are just starting the problem right as it is moving at 10 meters per second. If you throw something up into the air, right as that something is leaving your hand, that's when we're starting the problem. Not before, because that is a totally different problem. So, we said that this motion of this object is going to start off in the upwards direction. It's going to travel up, up, up. But as it travels up, it's going to move slower and slower and slower until it comes to a stop. And then it's probably going to speed up again in the same manner that it slowed down to get up there. And the reason for that is because there is a force on it. And that force we call the force of gravity. So that is Fg. Now that force of gravity is going to cause an acceleration. It's going to cause it to slow down on the way up. It's going to cause it to speed up on the way down, because accelerations that point opposite the direction of their velocities are going to reduce the magnitude, the amount of that velocity. Accelerations that are in the same direction of the velocity are going to make that velocity increase. Okay, so this ball on the way up is going to be slowing down. Of course, that makes sense. Acceleration is in the downward direction. Velocity, the motion, is in the upwards direction. We have to slow down on the way up. Once we are up here, we are going to start to speed up on the way down. Our velocity is pointing down. Our acceleration is pointing down from that force. And all the time that we are in the air, we are going to consider the acceleration to be a value of g. And the accepted value of g on Earth is going to be about 9.8 meters per second. And the accepted value in this class is going to be, squiggly, squiggly, approximately 10, because I don't really like pulling out my calculator unless I absolutely have to. So please accept that we're going to use 10 meters per second as our acceleration if we were in free fall. And this is a free fall problem. Okay. Also, because we have up and down motion to consider, this acceleration should be a negative because it is pointed on our negative direction if we denote our initial velocity to be positive. Okay, so on the way up, we start off with 10 meters per second. It stops eventually. The question right now that I have for all of you is how long does it take to stop? And so I'm not going to pause for too long because this is a pre-recorded video, but to go from 10 to 0, that is a change of velocity of negative 10 meters per second. Now, what we know about the acceleration definition is that that is literally a change in velocity over a change in time. And so a change in velocity of negative 10, if my acceleration is 10 meters per second, every second would take me a total time of 1 second to get all the way up here. Okay. Now, once we are up here, we are going to fall back down, and it just so happens that because it is the same exact acceleration value that is affecting this object, it's going to take another 1 second to fall back down. It is a very symmetrical thing if we ignore air resistance, which we will until you get to the calculus-based physics. That means that Carl, once again, is going to be at his starting location, although he will be moving not up, but he will be moving down at 10 meters per second. And we have already taken 1 second to go up. We have taken another second to come back down to the same position, and we have 1 more second to go, which means that he will be somewhere down here. I'm not sure where at the moment, but he will be down there, and he will be moving much faster because he is allowed to move for 1 more second. And if gravity affects you for 1 more second, that means we can tack another negative 10 on, and this 10 meters per second will turn into a negative 20 meters per second if we are allowing gravity to work for 1 more second in time. All right, now that begs the question, where the heck are we when we start off? Are at max height, and then we are at the very end, just before it hits any object or ground down there. And the way we can do that is we can simply look at what is called average velocity. And average velocity, as explained earlier, but I'm going to reiterate it again, is going to be the total change in position for that particular time, we'll use y in this case, over a change in time. Or, if we really want to think about it, it's just going to be the midpoint between 2 points given a constant change. That constant change is going to be this guy. This guy's a constant change. So if we start off at 10 meters per second and we end up at 0, it's like, you know, if you've probably calculated your average before. If you make a 0 and you make 100, what's your average? Well, that's a 50. They're equally weighted, right? So between starting point and maximum height ending point, the velocity on the average is going to be right in the middle, 5 meters per second. Okay, and that's going to be quite useful to us because all we need to do is rearrange this equation and just say, oh, well, if we rearrange the equation, the average velocity for the time taken to move should give me a change in position. And that's exactly what I'm going to look at. My average velocity for this first portion was 5 meters per second. The time allowed to get up there was 1 second, which means my change in position from beginning to max height is going to be 5 meters. Okay, so this change in position here is going to be maximum height of 5 meters beyond the cliff face, if this is 0. Okay, that's one thing we got to say. So from here to there, it's 5 meters. We're just going to call this 0 at the moment. Now, if we know we go from the very top back down to the very bottom, I know that my velocity at the very top started at 0. I know that my velocity at the very bottom is negative 20. And so the average between 0 and negative 20 is going to be a average velocity from all the way there to all the way down there. Make sure you know your points that you're talking about. The average velocity here is going to be negative 10 meters per second. Because, again, you make a 0, you got a 20, your average is 10. If your change is constant between those two marks, which it is because of gravity being constant. Now, I know that the time taken to go from here down to there is going to be 1 second and then another 1 second, so a total of 2 seconds from top to bottom. And so I can just run this equation again. The average velocity for this second half of my up-down is going to be negative 10 meters per second My total time of motion is 2 seconds, and that's going to give me negative 20 meters, which means from up here to all the way down there, that's a total of 20 meters. Because we know this top portion is only 5 meters, I guess to right there would be 5 meters, that means that this portion down here would be the rest, so that would be a 15-meter drop beyond the bottom of the cliff. So I'll put in negative 15. Okay, so that is very, very basic usages of displacement, distance, acceleration, average velocity, and all that good stuff. I'm going to stop this video right here.